we have few results theorem which are parallel to the theorem sequences. Just like in case of sequence, we have established some results, the sum of the limit of the sum of the sequence is the sum of the limits, difference, product, and like this. Similarly, the similar results holds good in case of the function. In fact, we have seen one result that if the limit of the function f x when x tends to c is exists say L, then it can be equivalently written in terms of the sequential form. That is, we can get the sequence x n which goes to c and x n is different from c, such that limit of this f of x n will go to L. So, all the results which are valid, the proof of all the results are exactly parallel as we have done in case of the sequences. However, we can also establish that proof with the help of epsilon delta definition. So, I am just stating the results without proof, because it runs as earlier as follows as by the on the same lines as we have used in case of sequences. Okay. So, results are, before going for the results, we define, of course, it is a very obvious thing, but still I will complete it. Let A is a non-empty subset of R, and let f and g be functions defined on A to R. Then the addition, subtraction, etcetera we define as follows. Then we define the sum of the two functions f plus g x as f x plus g x. The difference of this is defined like this, and the product of this is f x into g x. If b is a constant, then b of f x is defined as b of f x, where v is some real number r for some constant r real number, and if h x is not equal to 0 for x belonging to A, then we can define the sequence quotient f by h x as f x over h x for all x belonging to A, and this is also true for all x belonging to A. This is also true for all x belongs to A, all x belongs to A. So, this way we are defining. So, similar results, theorems also limiting theorems can also be written like this. Let A, which is subset of R, and let f and g be functions on A to R, and let C, which is a point in R, be a cluster point of A. Further, let B is a real number, any real number belonging to R, then the following result we can say: if the limit of f when x tends to C is L, meaning is that is limit of f x when x tends to C is L. So, I am dropping the x suffix. So, that limit is this, and limit of g when x tends to C is M, say, then then the limit of the sum f plus g x tends to c will be L plus m, limit of the difference will be L minus m, limit of the product f g as x tends to c is L m, and limit of this b f x tends to c is b times L. And further, if h is a mapping from A to R, a function, and if h is not equal to 0, h x is not equal to 0 for all x belonging to A, and if the limit of h exists, limit of h when x tends to c is h which is different from 0, then the limit of this ratio f over h when x tends to c is nothing but L by h. Okay. So, proof is okay. Now just goes on. Now, here we will make one remark. The remark is that in the part B, we have put a restriction that limit of h x when x tends to c should be different from 0, because if it is 0, then this limit is not defined. However, even that suppose f is also 0, h is also 0, then we cannot define the limit of f over h, because that comes out to be an indeterminate case. The limit may or may not exist. If it is, suppose limit of L is also 0 and h is also 0, in that case when you substitute the value or take the limit, it will come out to 0 by 0. You cannot say the limit is 1 or limit is 0, it may be anything. So, all may not exist also. So, what we say is then whenever this limiting behavior of the function f over h is different from 0, and particularly in the case of ratio, when they are different from 0, h is different from 0, then only we can say the limit exists, because if h is different from 0, even L is 0, the limit will come out to be 0. But if L is also 0 and h is also 0, then the problem occurs. So, we put this restriction on it. Okay. So, that is what we may not. Another note, so we can say note, suppose there are these functions which are defined on A and having, let f 1 f 2 say f n be a functions defined on A to R, and having, and C be the crystal point of this, and having the limiting values say L 1, L 2, L n respectively, when at the point limiting value at the point C, which is a cluster point of A, then the limit of this f 1 plus f 2 plus f n when x tends to C will be the sum of these limits, and similarly f n say f n. So, here n, and when you find the product of this, again when you take the, here it is I will say is fixed. So, here it should not be, suppose it is m, okay, m. So, here is also m, this is m, otherwise it will confuse because limiting value is taken is given. Okay. So, when x is 10, okay, is okay, then m, and this is m, and this comes out to be L 1, limit of this x tends to C comes out to be L 1, L 2, L m. And as a result, when all L 1, L 2, L n are same, then it comes out to be x to the power n, when these are all identical as a particular case. Now, let us see this few example based on this previous results, and we can suppose we wanted to show, say, limit of this, verify the limit of this x tends to say 2 x cube minus 4 over x square plus 1, or find the limit of this. Now, it is not asked to use the epsilon delta definition. So, what we do is, because it is of the form f x by h x is x square plus 1, which is different from 0 in the neighborhood of 2. Okay. So, obviously, we can use the result, we can find out the limit of this function, we can find the limit of this function and then value. So, when getting the limit of this function, substitute x tends to 2 means it will go to 2 cube minus 4 over 2 square plus 1, and that comes out to be 4 by 5. So, just substitute it, provided everything goes well. There is if I take the limit of this, say x square minus 4 over 3 x minus 6 when x tends to 2, find the limit of this. Now, here when you substitute x is 2, the denominator is vanishing. Okay. So, it will not define for that. Similarly, when you take x equal to 2, the numerator is also 10. So, basically it is coming to with the 0 over 0 form when you replace x equal to 2, which is known as the indeterminate case, indeterminate form, that we will discuss later when we go for the Euler-Spitzer rule in another, how to compute this limit of such a ratio which comes in the form of indeterminate. But here this is a function, very simple function, we can also use some trick to find out the limit of this. Obviously, when we say that x tends to say 2, the numerator is 0, denominator is 0. It means there must be one factor involving x minus 2 in the numerator as well as x minus 2 in the denominator, then only numerator and denominator both are tending to 0. So, remove that x minus 2 factor. So, if I write the function x square minus 4, 3 x minus 6 for x different from 2, then what happen? You can write this thing as x plus 2 over 3, just because x minus 2 get cancelled. And then when you take the limit of this now, as x tends to 2, it is the same as limit x tends to 2, which comes out to be 4 by 3, and that answer is. Okay. So, that way we can easily find. Now, third is, if suppose p is a polynomial, if p is a polynomial of degree n, that is p x is of the form real polynomial of degree n. So, it is of the form say a n x to the power n, a n minus 1 x n minus 1 plus a naught, where a 1 a 2 a naught a 1 a 2 a n, these are all real numbers. Okay. X belongs to R. So, p x is a polynomial of degree n. If we are interested in computing the limit of this p x when x tends to c, then obviously, it is a sum of these functions, because each one is a function. So, when you take the limit of this as x tends to c, then x to the power n will go to c to the power n. So, it will come out to be the a n c to the power n plus a n minus 1 c n minus 1 plus a naught, which is equivalent to the polynomial p at the point c, a constant p c. So, limit of the polynomial p x when x tends to c is this. Then, if suppose we have a two polynomial p x and q x, if p x and q x are the two polynomial, then if p x and q x are polynomials on function polynomials on R polynomial functions on R, and if the polynomial at the point C, Q polynomial at the point C is different from 0, has a value different from 0, then the limit of this ratio P x over Q x when x tends to C is equal to P C over Q C. Okay. So, what we do here is we sorted out for the point. P x is a polynomial of any degree say n, and Q x is a polynomial of degree say m, and it is given the Q at the point C is different from 0, but that it does not solve our problem. Why? Because we know Q x is a polynomial of some degree. Okay, say degree, say suppose I take say m. It means it will have at most m roots. So, it will have m roots, some may be repeated, some real, some complex, like this. It may have m roots. It means at these roots alpha 1, alpha 2, alpha m, at this point at these roots the value of Q must be 0. I am assuming all the roots be distinct and real, say distinct and real. So, Q must be 0. So, it means when you approach to C, then path should not contain this point, because if it contains this point, then you cannot find the limit of Q x when x tends to C. So, what we do is we separate out, we take the choose x which is not in this set alpha 1, alpha 2, alpha, which is different from this. Okay. And then this x is tending to C. So, obviously, if I choose all the point in the neighborhood of the delta neighborhood of C, which does not involve these points, then the limiting value of Q x when x tends to C must be great. Then the limit of g x when x tends to C, in that case it is equal to g x, and g x already given to be non-zero. So, this one. Then C, once it is non-zero, then you can apply this result and get this. Okay. So, when you are very careful when you find the limit of this P x over Q x, the point should not be available where the Q has this one roots. Those points in that neighborhood, all the roots of the Q x must be out, then only you can get the limit of this. Okay. So, that is the one thing which we have. Now, this result is also interesting. The result says let A, which is subset of R, and let F which is a mapping from A to R, and let C belongs to R, be a cluster point, be a cluster point of A. And suppose if A is less than equal to f x, less than equal to b, means the all the images of f in the neighborhood of the C lies between this, f x of all x belongs to A and x is not equal to C. All the point f has a image over the set A except at C, which lies between A and B. Then, and if limit exists, and if limit of this f x as x tends to C exists, then the limit of this f x when x tends to c will lie between a and b, means the lower bound cannot be f x, limit of f x will lie between the two bound a and b. So, what it says is, if suppose we have this set a, here is some c and this is our function f, this is a function say f. Okay. There it has a lower bound a and this is a upper bound b for this function, maybe something like. So, what he says is that if all the images f x lies between a and b and function is also have a limit at the point c, then the limiting value of this say L will lie between a and b. That is what he said. So, proof is simple. Assume that given f is the limit, let L is the limit of the function f x when x tends to c. This is given, okay, because limit exists means this will be given. Okay. Now, as we have seen that limiting epsilon delta definition in sequential way convention way is also the same. This means we can also define the limit of the function by means of sequence, and the sequence limit says that this result, if I go through what this result says, this is equivalently we can say for every sequence, x n in A, every sequence x n in A that converges to C, such that x n is not equal to C, for all n belongs to natural number, then the sequence of the functional value f of x n, this sequence converges to L. So, when we say the limit of the function f x when x tends to c is L, the equivalently we can also say that there will be a sequence x n in A, means x 1, x 2, x n, these are available in this, or from here also, which are different from C. Then the corresponding images f x 1, f x 2, x f n, this sequence will converge to L. This is the way, equivalent definition of this. So, using this definition we can now prove like this. So, let us suppose a sequence x n in A exists that converges to C, but all the point x n is different from C, then the corresponding f x n will converge. Now, what is given is that f x will always lies between, this is given, f x always lie between A and B, but given is it is known that the f of x will always lie between these two bound for all x belongs to A and x is of course not different to C. Now, here x n is in A, but they are different from C. So, for such x n this value f of x n will also lie between A and B, is it not. So, when this two bound is there, so when you take the limit of n as n tends to infinity, this sequence f x n will go to L and this will bound lie between A and B. So, limit of f x n when n tends to infinity below that is the A is less than equal to limit of f when x tends to C is less than equal to B, and that proves the result, is it not. That proves the result, is okay. We have another result which is the skews theorem. Just like as in case of sequence we have shown, that similarly for functions also we have the theorem which is known as the skews theorem. Skews theorem. What this theorem says, let A is a subset of R, non-empty subset of R. Let f g h is a mapping from A to R, and let C be the crystal point. C belongs to R with the crystal point of A. Point of A. Now, if this inequality holds, f x is less than equal to g x is less than equal to h x holds for all x belonging to A except say C, x is not equal to C. And if the limit of this, if the limit of f as x tends to C is L, which is limit of h x when x tends to C. Both the limits exist and have the same value, say L. Then this Squeeze theorem says the limit of g x when x tends to C will also be L. Okay. So, this was proved earlier also, and even it follows from the previous result also, because the limit of this is L, limit of this is B. So, A and B are there, and this g x always lie between A and B for all A, is it? So, therefore, by Squeeze by previous result also limit will exist, and since both are equal left hand A and B are, so this limit will also be Squeeze all. Otherwise, also g x minus f x you can write it, and h x minus we can get the results for it, okay, like this. So, this is nothing to much prove. Let us see the use of application of the Squeeze theorem, where we can apply the Squeeze theorem to get the limit of a functions easily, quickly. Suppose I say, so that limit of this, limit of x to the power half when x tends to 0 is 0. We have already seen when x to the power n, when n is a positive integer, then it can be written x into x, x into x up to n, and limit x tends to 0, it will be 0. But when this power is not integer, then x raised to y is fractional, then you can not write in the form of x into x or something like that, we do not. So, we have to show that, of course, this will be discussed when we did for the Cantor's theory another, that x to the power alpha, alpha is rational, alpha n is a sequence conversion, then alpha will go, that is already discussed, but still we using this Squeeze theorem we can prove this. So, how? So, suppose f x is basically x to the power half for all x, this is we want 3 by 2, let it be 3 by 2, okay, for this x is greater than 0, x is greater than 0, sorry. So, that this is greater than, now f x is 3 by 2, when x is positive, it is positive throughout. Now, we have this since x is less than x raised to the power half, which is less than 1 or maybe at the most equal to 1, holds for 0 less than x less than equal to 1. This result is true. So, if I further multiply by x, then multiply by x, multiply by x, because x is positive. So, it will not reverse the inequality. So, what we get it, x square is less than x raised 3 by 2 is less than equal to x. Now, apply the Squeeze theorem. Here the f x is this, which tends to 0. This g x h x is also a which tends to 0 as x tends to 0. Therefore, limit of this has to go to 0. So, this proves the result. So, this shows that by Squeeze theorem limit of this x raised to the power 3 by 2 as x tends to 0 is 0.